The nucleus of an atom, which consists of protons and neutrons. Orbiting or revolving around the nucleus are negatively charged electrons which behaves in an unpredictable manner. Ever wonder how to locate an electron? Can we actually locate an electron? Where exactly is an electron in an atom? Now, let's recall back during SPM. We have learned about electron arrangement using the 2-8-8-2 notation. Here's an example. This is lithium, a neutral atom that has 3 electrons. So, its electronic configuration would be 2.1. Simple? Easy lah. This is before quantum chemistry comes into the picture. Now, as you get older, you learn about the microscopic miniature of quantum world. So we should be asking yourself on how to specifically locate an electron and describe its movement and trajectories within an atom. Because you'll soon learn they are negatively charged for a reason. So, how do we describe an electron in an atom? What sort of sorcery does a chemist use to locate an electron within an atom? We chemists use specific 4 sets of numbers called the quantum numbers of electron. Just like telling your best friend the whereabouts of your crush in a place on Earth, that goes to say on how to explain the whereabouts of an electron by using the quantum numbers of electron. So before we begin about explaining more further about quantum numbers, we need to know the region or space that electrons are associated with, which is called an orbital. So, what is an orbital? To put it in scientific terms, an orbital is a 3-dimensional region in space around the nucleus where there is a high probability of finding an electron. To put it in simpler terms, think of it as orbital as a place where electrons love to hang out. Like for example, the highest probability of finding nowadays teenagers is at Starbucks. That goes the same with electrons. So, an orbital is like a living place where electrons live in. This video shows an example of an atomic orbital. This is an example of an electron orbiting the nucleus. However, this is not exactly the truth. It is almost impossible to precisely locate an electron. The best way to do it is to predict where can an electron be found within an atom. This is where orbital comes in. The blue areas around the nucleus is the orbital that we are describing. An electron will occupy an orbital until it is completely filled. Once it is completely filled, the next electron will occupy the next shell. The next shell represents a next energy level, thus increasing the size of orbital as well as in terms of energy level. You will also soon learn how to draw shapes of other types of orbital that governs the quantum numbers of electron. In order to describe these orbitals in which electron can be found, we use a specific 4 sets of numbers spawned from the molecular orbital theory of Frederick Hahn and Robert S. Mulligan. Feeling amazed yet? You should feel amazed, because this is probably the only time that you'll feel amazed. Here are the maths. Quantum numbers of an electron. Throughout this video, we will only be covering the basic of quantum numbers of an electron. We must remember that these 4 main quantum numbers are used to describe the probable location of an electron in an atom. These quantum numbers are characterized by a set of 4 quantum numbers that are n, l, m, and s. So the first quantum number is the principal quantum number that describes the shell or energy level of an atom. It also describes the size of an orbital, which correlates with the energy level. What it means is that as the energy level increases, the size of an orbital also increases. Next is the angular momentum quantum number, which is the second quantum number. It describes the shape and types of orbital. The angular momentum quantum number also represents the subshell within an orbital. It is also known as azimuthal or subsidiary or orbital quantum number. These are some of the examples of the shape of orbitals that you will encounter. The first shape is the spear shape, which is associated with the s orbital. And the second shape is a dumbbell shape, which is associated with the p orbitals. Next is the magnetic quantum number, which is the third quantum number. It indicates the orientation of orbital in space around the nucleus and distinguishes orbitals within the subshells. What this basically means is that the magnetic quantum number describes the energy level available within a subshell. The last but not least, the fourth quantum number, which is the spin quantum number. It describes the angular momentum of orbitals, and there are 2 possible motions, clockwise and anti-clockwise. you must always remember that the S value of the spin quantum number will always be it's either positive 1 over 2 or negative 1 over 2. With every given formulas or anything, there will always be a rule behind it to apply. These are the following rules that governs each quantum numbers. The first thing that you have to note is that the three quantum numbers, N, principal quantum number, L, angular momentum quantum number, and M, the magnetic quantum number, these three quantum numbers must be described as an integer and it cannot be in terms of a fraction or any other given mathematical wave function. The second rule is that the principal quantum number cannot be zero. Cannot be zero. Allowed values for a principal quantum number should be starting from 1, 2, 3, and so on. The third rule is the angular momentum quantum number can be any integer between 0 and n minus 1. N represents the principal quantum number, which means the energy level minus 1. So for example, if you have your energy level equals to 2, the allowed value for your L is L, 0, and 1. Your subshell is also categorized by two ways. Number 1, through the numbers 0, 1, 2, 3, and the subshell is represented by alphabet S, P, D, F. The third rule is that the magnetic quantum number can be any integer between negative L and positive L. The magnetic quantum number is highly influenced by the angular momentum. So the allowed values for the magnetic quantum numbers is the integer between negative angular momentum and positive angular momentum quantum numbers. So for example, when your angular momentum quantum number is equal to 1, your allowed values of M are positive 1, 0, and negative 1. Why is there a 0 here? Because it can be any integer between the numbers that are given for the angular momentum. Are you still that blurry? You still confused? I bet you are. Don't worry, keep calm and let's practice. Let's do this. Go right ahead and try the tutorial questions on your own. Don't forget to click subscribe and turn on your notification.